You ever run into a problem that's just so complex, so full of possibilities that finding the perfect answer feels, well, impossible? Turns out, a ton of real-world challenges, from logistics to scheduling, are exactly like that. So in this explainer, we're going to dive deep into what makes these problems so incredibly hard and how we can even begin to think about tackling the unsolvable. Okay, to get a feel for this, let's start with a classic. It's called the traveling salesperson problem. The goal sounds simple, right? Just find the shortest possible loop that visits a bunch of cities exactly once. For 15 cities, that sounds pretty doable. I mean, your laptop could probably just check all the options really fast, or could it? So, what do you think? For just 15 cities, how many unique round-trip paths are we talking about here? A couple thousand? Maybe a million? Nope. The answer is over 43 billion. Let that sink in. Even if your computer could check a billion routes every single second, it would still take almost a minute to check them all. And here's the crazy part. Add just one more city, and that number explodes into the trillions. This insane rate of growth has a name. It's called combinatorial explosion. And it's the number one reason why the brute force approach, just trying every single possibility, is a complete dead end. The number of options just grows way too fast for any computer we have today or any we can even imagine. All right, so if we can't just power through it, how in the world do we solve these problems? Well, the first step is to really understand what we're up against. We've got to name this dragon of complexity before we can figure out how to fight it. In computer science, we basically sort problems into two big buckets. On one side, you have P problems. Think of these as the easy ones, because a computer can find a solution really fast. Getting directions from point A to point B on a map, that's a P problem. But our traveling salesperson problem, that falls into the NP bucket. For these problems, finding the best solution can be incredibly slow. But, and this is the absolute key, if I just gave you a route and said, hey, is this route under 500 miles? You could check that answer in a flash. Easy to check, hard to solve. And then you have the final boss level, NP hard problems. These are the real titans, the toughest nuts to crack. And our salesperson problem is one of them. What's wild is that they're all connected. If you could somehow find a magical, super fast way to solve just one of these NP hard problems, you would instantly have a fast way to solve every single problem in NP. This whole puzzle is actually one of the biggest unsolved questions in computer science, whether P equals NP, and there's a $1 million prize waiting for whoever figures it out. So before we can even point an algorithm at a problem, we have to do something absolutely critical. We have to take the messy, complicated real world and translate it into a clean, structured language that a computer can actually understand. This whole process is called modeling. A good model really comes down to three things. First, you need decision variables. You can think of these as all the little switches and levers the algorithm gets to play with. For our route, every possible road between two cities gets a simple yes or no switch. We can just use a 1 for yes, take this road, and a 0 for no, don't. Next, you need constraints. These are the rules of the game. They're what makes a solution valid. For our salesperson, the big rules are pretty clear. You have to visit every single city, and you can only visit each one once. No skipping towns and no doubling back. Simple as that. And last but not least, you need an objective function. This is the end game. It's the one single number you're trying to make as good as possible. For our problem, it's super clear. Add up the distances of all the roads we chose to take, and our goal is to get that total number as low as we possibly can. That's the score the algorithm is trying to beat. Okay, so we've got our problem beautifully defined, but we still can't check all 43 billion possibilities. So what now? Well, the solution isn't to work harder, it's to work smarter. We need a clever divide and conquer strategy. Here's the core idea, the secret sauce, really. Instead of just blindly checking every path one by one, we can be way more strategic. The goal is to explore this huge landscape of possible solutions, but, and this is the magic part, intelligently throw away entire chunks of it that we know for a fact can't possibly hold the best answer. And one of the most powerful ways to do this is a technique called branch and bound. It's like a cycle. First, you bound. You take a set of choices and get a quick, super optimistic estimate of how good the final solution could be. Then you prune. You look at that optimistic guess and compare it to the best actual solution you've found so far. If your best-case scenario guess is already worse, you just chop off that entire branch of possibilities. Millions of potential routes, gone. Just like that. But if it still looks promising, you branch. You split the problem into smaller choices and start the whole cycle over again, going deeper and deeper. It's this clever process that lets us find the perfect answer without getting crushed by that combinatorial explosion. Now, even with these incredibly clever methods, finding that one provably perfect solution can sometimes take a really, really long time. And this brings us to a huge question in the real world, the battle between a perfect answer and a practical one. This is where knowing a problem is NP hard is so useful. It tells us which tool to pull out of the toolbox. We can use exact algorithms, like we just talked about. They promise the perfect answer, but they might take forever. Or we could use approximation algorithms that get us an answer we know is, say, within 10% of the best one. And very often we use heuristics. These are just smart shortcuts, clever rules of thumb that find really good answers really fast, with no promises of perfection. And that right there is the fundamental trade-off. Do you absolutely positively need the one true guaranteed best answer? Maybe it's for a multi-million-dollar decision where every fraction of a percent matters. If so, you need an exact method, and you'll just have to wait. But what if you're routing 1,000 delivery trucks that need to be on the road in 5 minutes? In that case, a heuristic that gives you a 99% perfect answer right now is infinitely better than a 100% perfect answer that shows up tomorrow. And that leaves us with this final, really important question. The quest to solve these hard problems isn't just a hunt for the perfect algorithm. It's really about understanding these trade-offs. It forces us to step back and ask, in a world with limited time and limited resources, how do we even define what the best choice really is? Definitely something to think about.